Now, the third type of hydrogen bonding is actually a type of dipole interactions. But because it's such a big deal, we're just going to treat it as its own little category here. So number three, the third type of intermolecular forces, hydrogen bonding. So guess what element it involves? Hydrogen. But it also involves hydrogen that's attracted to a very electronegative atom. And the ones that we're going to focus on are nitrogen, oxygen, or fluorine. Those are the strongest kind of bullies of the whole periodic table. These are the ones that pull electrons away from whatever they bond with so much that it ends up with a partial negative charge. And if they pull electrons away and end up with this charge, well, poor little hydrogen, who doesn't win many battles, always ends up with a partial positive charge. These guys, you can imagine, are going to be attracted to each other. That attraction is called a hydrogen bond. Why? Because it involves hydrogen. So if we look over here, look at these molecules. This red atom here represents oxygen. This gray one represents hydrogen. So oxygen has a 3.5 for an EN value. Hydrogen's only a 2.1. There's a big polarity difference here. Hydrogen's electrons move up towards oxygen. So poor little hydrogen. This one, it's in the same boat. Electrons move away. This guy, electrons move away. All of these hydrogens keep losing their electrons, and they all end up with these partial positive charges. And they're attracted, because they're so positive, they're very attracted to these neighboring negative ones. The ones that are so strong that they pull the electrons towards it, they end up with a partial negative charge. So these two are attracted, and you can see that they're represented by dashes here. That's representing a hydrogen bond. The straight lines, those are real bonds, but the dashes are the intermolecular forces. Over here, good old water. Water's, remember the oxygen pulling the electrons up. Electrons end up there. They end up away from down here. So this poor little hydrogen is losing its electrons. It's becoming partially positive. But this bully oxygen is gaining electrons, so it's becoming partially negative. So this partial positive hydrogen is attracted, again the dotted lines, attracted to the top of the water molecule that it's neighboring. That attraction, remember it's not a real bond. We don't draw solid lines like we do within the molecule, but this is an inter between neighboring molecules. An intermolecular force called hydrogen bonding. So it's always involving hydrogen that's bonded to a very electronegative atom because it loses its electrons, it becomes partially positive, and then it's attracted to an unshared pair of electrons on a neighboring atom. So this guy here has got some electrons, it's negative, and it's pulling the electrons up, so it's very negative, and that's that attraction, that hydrogen bond. So if you don't see hydrogen, it's not hydrogen bonding, but it'll involve hydrogen. Again, here's another image, kind of what you just saw before. Oxygen, very electronegative. The neighboring hydrogen, very positive, and that's your hydrogen bond. Negative oxygen, positive hydrogen, there's another hydrogen bond, and so forth. And that happens all throughout the molecules. So it always involves hydrogen. And why? Well, hydrogen doesn't have a lot of a shielding effect. Remember we talked about kids in the way, or rows of electrons interacting between the valence electrons way out here and the protons. These electrons would be in the way. Well, hydrogen doesn't have any. It's only got one energy level. Remember the 1s1? Oops, 1s1. So there's no other electron shielding the proton from that. So that's why hydrogen loses its electrons so easily. It always ends up with this partially positive charge, and that nucleus is therefore, like over here, this nucleus of the hydrogen is attracted very easily to this nucleus of the nitrogen, or the electron cloud of the nitrogen. So the positive nucleus attracted to the electron cloud of the nitrogen. And there we go, there's your hydrogen bond. So this is why we could take ammonia and put it in water and it dissolves, it interacts with the water, because they're both polar. And there's that hydrogen bonding that takes place. And this is very much so responsible for the properties of water. Take a look at this diagram. Every hydrogen is attracted to the neighboring oxygen. And this attraction, depending on how much energy these guys have, if they're wiggling a lot, then that attraction isn't as strong. But if they're not wiggling as much, if they don't have a lot of energy, if they're pretty cold, then that attraction's stronger. And that'll determine the properties of water. And the second half of this section is all going to be about water, and it's primarily because Water's polar, and we got this hydrogen bond interactions between neighboring molecules. A couple other real-life examples. DNA. You wouldn't be here if it wasn't for these hydrogen bonds. DNA holds the two halves of this double helix. You learned about this in bio. But these sides of the DNA helix, again, are attracted, held together by these hydrogen bonds. Proteins. Here's a crazy looking protein. But every time you see these little dashed lines, little dots here, those are hydrogen bonds. So again, this coils and forms certain shapes because of those hydrogen bonds. And finally, it determines what substances do and don't interact with water, because water has hydrogen bonds. So if something like oil, which is nonpolar, it doesn't have any strong positive or negative ends, they don't exist, and water has them, there's no way to form hydrogen bonds with these particles, these nonpolar particles. So you see all the hydrogen bonds forming, all these red dashed lines, and we can't form them up here because there's no difference in polarity. And that's going to bring us to the next half of the notes, and it's all going to be about water. And it's primarily because water is polar and because it's got hydrogen bonds.